Hey, how's it going? This is Alex Zimmerman for my ENME 351 video lab series. This week we're doing lab 4, which is the sampling and aliasing lab. First off, we're going to take a quick look at my Arduino code. Two serial.begin statements, for one's used for debugging and an output to the serial monitor, where the 115,200 baud is used for the output to the processing. Then just looking at my code, my sampling frequency as my input is an analog input, as well as my n-scope value, which is also an input. The potentiometer has to be positioned just right to get the actual sampling frequencies that we want, and it can be a little bit finicky. Moving on to my images. Got it. As you see, I have this little table here, split up by, or organized by sampling frequency versus input frequency. 500, 200, 142, and 100 hertz are our four sampling frequencies, and our four input frequencies are 75, 100, 215, and 300 hertz. Just looking in at the 75 hertz, as you can see, we have our output frequency at the bottom, as well as our plot on the top, all oscillating roughly between 0 and 5 with a DC offset of 2.5 volts on all of them. All of the graphs where the frequency is 2 times the frequency is less than the sampling frequency will not have an aliasing. So there's no aliasing frequency for these two graphs, or for this graph. So where 215 hertz, 100 hertz, and 75 hertz are sampled at 500, and where 100 hertz and 75 hertz are sampled at 200. All of the others do have an aliasing frequency, which can be found at the bottom part of the graph. Moving on to our data table, we have our desired values and the actual values. As I mentioned, the potentiometer, I had to be very exact, so not all of my actual values are as close to the desired values as I would have liked. However, this lab video is coming in a little bit late. My delay over sampling time, all rough values roughly of 1, and then my Nyquist frequencies, which are half of the VSA value. Then I have my 4 input frequencies, 75 hertz, 100 hertz, 215 hertz, and 300 hertz. The Nyquist rates is just going to be 2 times this frequency. My experimental alias frequency is just the data that I took from the images above, and the theoretical is calculated using this. The sampling frequency times a whole integer minus the actual value from the VSA. All of the theoretical versus experimental calculations are all very close. As you can see, this only one outlier right here with the difference of 11. This 54 and 46. All right, now we're going to look at exercise 2 and the square wave and sine wave. As you can see right now on my n-scope, I have a square wave oscillating between 0 and 5 volts at 10 hertz. Here's just the circuit showing, working right now. P1 allows me to do this square wave, and here it is outputting to the processing code, showing a square wave with a decreasing voltage based on frequency. If I switch this P1 input to A1, I will change the graph to a triangle wave. If I pull up my Word document here, you can see my square wave, which has more data points on the spectrum plot than the sinusoidal waves at the top, or in exercise 1, and then as well as the triangle wave, there are a few more plots on the spectrum plot as well. That is all that I have for this week's lab. Thank you. Have a good one.